Our next talk is by Jon Blitz, also from Quantum, Synthesis and Characterization of Model Silica-Supported Polymerization Catalyst.
Today, I do want to talk about some work that I've been doing the past year or two concerning the modeling of silica-supported coordination polymerization catalysts. Quantum's bread and butter is in fact cyclovinyl acetate, polyethylene, homo and copolymers. So we use coordination polymerization catalysts extensively to make our various polymers. And a lot of times they are in fact supported on silica for various reasons. You may be wanting to know exactly what I'm trying to do with this, being an industry, and it turns out that it's sort of an academic project. In that what I'm trying to do is follow down the road of many scientists interested in heterogeneous catalysis and trying to correlate molecular level structure with catalytic properties. And as I'm sure most, if not all of you know, that's an easy thing to do, easy thing to say, but it's almost an intractable problem in reality. I have deluded myself, and hopefully I'll delude you, that I have gone a little bit, just a little bit, towards trying to achieve that goal in a specific sense. And the way I've conceptualized this project may be a little bit different from what other people have done, and it reflects my background, I think, in the characterization of chemically modified surfaces. And so the way I look at these polymerization catalysts, supported metal polymerization catalysts, is simply as a chemically modified surface in need of characterization. And so the first question I think about is what is the surface chemistry of silica? What kind of functional groups are on there to do chemistry with? And then what I'm going to want to do is to modify the surface chemistry of silica by various treatments in order to change those types of functional groups in order to do subsequent reactions. And in this way, hopefully, be able to synthesize species of known surface structure and be able to vary the structure in order to correlate the structure with the catalytic properties. That is the road that I'm going to take. The outline of the talk is as follows. I rely heavily on infrared spectroscopy. I have some expertise in the area, and I also have unlimited spectrometer time. So whatever I can do by infrared spectroscopy, I do. If I can't do it, then I beg and plead others to help me out to carry out other analyses. And I'm rapidly finding out that the diffuse reflectance technique is being more widely used than it was a few years ago, so I'm not sure that it's necessary, but I'll put up a quick slide on exactly how the technique works physically. I'll then talk about the conventional wisdom of what kind of surface functional groups are on silica and how you can modify them by either chemical treatment, that is reaction with organosilanes, or thermal treatment at various temperatures. I will then take these modified silicas by either chemical or thermal treatment and react them with titanium tetrafluoride. These catalysts that I'm looking at are Ziegler-Natta catalysts, silica-supported Ziegler-Natta catalysts, which are a broad definition might be a combination of a transition metal halide with a metal alkyl. And titanium tetrafluoride is the classic transition metal halide, which is used in Ziegler-Natta catalysts. And at the end, I'll be talking about triethyl aluminum and the aluminum alkyl, which is also a fairly standard thing. And in order to get information on these titanium tetrafluoride reactions with silica, we have to get some information in regions which are generally inaccessible because of silica gel matrix absorptions by transmission infrared spectroscopy, which is where the diffuse reflectance technique comes in this work. And finally, after doing all these things and then characterizing what types of bonds there are with titanium with the surface, I'll show a couple of polymerizations to try to correlate the structure with the catalysis. Now quickly, specular, and here's how the diffuse reflectance technique works. You have a powdered sample. The diffuse reflectance technique allows you to take Spectra powdered samples. We take silica gel or the modified surface or whatever we've done to it and disperse it in potassium chloride at a 10% by weight. And place it in a sample cup, controlled atmosphere and whatnot, because these are very air-sensitive catalysts. And here I've depicted the infrared radiation coming in. And surrounding this is simply a commercially available accessory with lots of mirrors that you can tweak up to get a good signal. And okay, we have the infrared radiation coming in and some of it bouncing off at the same angle. That's the specularly reflected radiation. We're not interested in that. And so the optics just takes that radiation and throws it away. The diffusely reflected radiation, that is the radiation that gets scattered, undergoes multiple reflections, refractions, and diffractions with various particles in the sample, and therefore interacts with the surface to a fair extent and contains the spectroscopic information. And then the optics then takes this, at least part of the scattered radiation and focuses on towards your infrared detector back in the spectrum. In terms of what is the conventional wisdom of what the silica surface looks like these days in terms of functional groups? Silica gel, the matrix is, of course, made up of SiO2 or SiOSi siloxane bonds. These are generally unreactive and they just hold the material together. The surface, however, is terminated with various types of functional groups, all silanols. There are single silanols which are removed, enough far removed from other silanols such that they undergo no hydrogen bonding, essentially no hydrogen bonding interactions. And then there are other single silanols which are close enough together to hydrogen bond. And then there are the ever-present controversial geminal silanols, that is the two silanols on a given silicon. And they may be hydrogen bonded or non-hydrogen bonded depending on their present place in proximity to other silanols. But in terms of infrared spectroscopy, what we detect are hydrogen bonding interactions. So the model which I'm going to show of the silica surface is just, I'm simply going to talk about non-hydrogen bonded silanols versus hydrogen bonded silanols and differentiate the groups in that way. And the geminal silanols are implicit in here, but I'm basically going to ignore them. Now there's a number of ways to react these silanols. One very convenient way which we've been using is to react them with an organosilane. Here you have a silica, S stands for surface, silica surface silanol. And you can react the silanol with an organosilane. Here we use hexamethyl, 6 methyls, and here's a silazane linkage. So we call it hexamethyl disilazane, or HMDS. This will react with the silica surface to form a new siloxane linkage capped with a 3-methyl group. This would be a trimethyl silyl group. And then you get reaction products. I want to show a spectrum of what these things look like, silica surfaces look like. Here are a couple of drift spectra. The y-axis is, you don't need to worry about it, it's essentially absorbance. You can think of it as, it's analogous to absorbance and transmission, so transmit spectroscopy. And here's the region which we're looking at up here in the OH stretching region of the spectrum. Unmodified silica gel. This is just silica gel heated to desorb the physisorbed water from it. Here's the band at 3745 from non-hydrogen bonded silanols, and then 2 bands at 3660 and 3540 from hydrogen bonded silanols. After reaction with the hexamethyl disilazane, you see that the band at 3745 wave numbers has disappeared. But the 2 bands from hydrogen bonded silanols remain intact, and here is the CH stretching absorbance from the trimethyl silyl groups from the HMDS. So interpretation of that reaction is relatively straightforward and kind of convenient. If you take our model silica surface and react it with hexamethyl disilazane, it reacts preferentially with the non-hydrogen bonded silanols to cap those with trimethylsilyl groups, and the hydrogen bonded silanols remain intact. So we can do chemistry on that later on with the titanium tetrafluoride. The second way to modify or pre-modify the silica surface is to have it undergo thermal treatment. Here's some results of some in situ variable temperature drift studies of again, an unmodified silica gel as temperature is increased in this direction. At low temperature, here you see the desorbed water is initially desorbed. Between about 300 and 500 degrees C, the two bands that from hydrogen bonded silanols begin to disappear. They condense out and split out water in new siloxane linkages. And 600 degrees C is the magic number. This is the temperature at which you have a very high concentration yet of non-hydrogen bonded silanols, but the hydrogen bonded silanols have all condensed to split out water. And above this temperature, you start really doing some severe things to the surface. So in terms of the model of the surface, if you take your silica gel with non-hydrogen bonded and hydrogen bonded silanols and hit it at 600 degrees C for a few hours, these condense to split out water. You get the new siloxane linkage, and then you have the non-hydrogen bonded silanols left to do chemistry on later. So let me just summarize what we've done so far. You have your silica gel. Here's our hydrogen bond. You have your silica gel with non-hydrogen bonded and hydrogen bonded silanols. React it with an organosilane, and you end up with a surface with hydrogen bonded silanols for subsequent chemistry. Take the same surface and treat it at 600 degrees C, you have non-hydrogen bonded silanols left for subsequent chemistry. Now we want to take these surfaces and react them with titanium tetrachloride to see what happens. Here's a drift spectrum in the entire mid-infrared region, which is accessible to us. What we've been doing, and what has conventionally been done in the past by transmission spectroscopy, is to focus in on this region here. And the reason for that is that when you press a pellet of these silica gels, once you get below here, you have a completely absorbing sample and you can't get any more information down there. But it turns out that if you want to really characterize reactions of these transition metal halides with silica, what you want to do is look at silicon oxygen, in this case titanium bonds. And unfortunately, they're going to fall right around in here, which was previously inaccessible. But with the surface selectivity of the diffuse reflectance technique, hopefully by spectral subtraction, we can start to obtain some information in that region. Here are some spectra with that region focused in on between 1200 and 700 wave numbers. Here's the silica gel, the SiOSi asymmetric stretch of the unmodified silica gel before and after reaction. If you just look at these two, you don't see a whole lot of difference. But you do spectral subtraction. What I'm doing is nulling this band here at 800 from the symmetric stretch of silica. The two bands appear, one at 990 and one at 920 wave numbers. And this negative going peak is not an artifact. It's in fact a result of a reaction of silanols. There's a silanol band in here as well, so that's real. So the question is, what are these two bands at 990 and 920 wave numbers? The way went about doing that is first, of course, went to the literature and then reacted titanium tetrachloride with the pre-modified silica gels, as I've been describing. And here's that same spectrum of the unmodified silica gel, the band at 990 and 920 wave numbers. Now, if we take the hexamethyl disilazane modified silica gel and react it with titanium tetrachloride, we get a band predominantly at 920 wave numbers. Now remember, the hexamethyl disilazane selectively modifies the non-hydrogen bonded solenols to leave you the hydrogen bonded solenols. And if you take the 600 C pretreated silica gel and react it with titanium tet, you get a band predominantly at 990 wave numbers. Rationalizing this in our minds and looking up some, there have only been 2 previous works really in terms of infrared reactions with silica gel. Putting all this together, we've assigned the 990 band to this type of species, a singly bonded SiOTi to the surface, and the 920 band to what I'm calling a bridge bonded titanium to the surface. So just to make sure that you remain with me, I want to review now the titanium tetrachloride reaction with the silica gel. Here we have the unmodified silica gel, and react it with titanium tetrachloride, you get the bridge bonded and the singly bonded species, bands at 990 and 920 wave numbers. If you take this silica gel and pre-treat it at 600 degrees, you condense the bisphenol or the hydrogen bonded solenols, then react with titanium tetrachloride, you get the predominantly singly bonded species. On the other hand, if you take your silica gel and then react with the organosilane, it selectively silylates the non-hydrogen bonded solenols. Take that and react it with titanium tetrachloride, you get predominantly the bridge bonded species. So what we've been able to do at this point then is to essentially make different types of catalysts and characterize them with either 1 or 2 bonds to the surface. And the question then is, okay, that's great, let's do some catalysis finally and see what the differences are. The first thing we did was to do some ethylene homopolymerization. That is, just take ethylene, well, first of all, I take the silica gel, react it with the titanium tetrachloride, slurry it up in hexane, and react it 3-to-1 molar ratio with aluminum triethyl to the titanium on the surface, which we analyzed by XRF. And then just bubbled ethylene through it. In red is the singly bonded catalyst. These spectra here are simply spectra of the polyethylene, which is made by the polymerization. And you see that in both cases, there's no band at 1378 wave numbers. You'll see that band in the next slide. And that's for methyl groups. You would expect to see those bands if there was some short chain branches off the regular chain, or if it was a very low molecular weight type of polymer. And you see in both cases that it's probably a very linear polyethylene, very high molecular weight. The surprising thing, or the interesting thing, maybe not so surprising, but the interesting thing is that the activities are very different. The singly bonded catalyst gives an activity of 165 grams of polyethylene per gram of titanium per hour of the reaction, whereas the bridge bonded catalyst gives an activity of about 45 grams of polyethylene per gram of titanium per hour. I've also included the DSC melting point of the polymers, both at 133 degrees C, indicating once again a very high molecular weight, not very branched polymer. So in terms of the products are essentially the same, but the activities are very different depending on what you start with in terms of the bonding of the titanium to that surface. The next thing we did was a ethylene 1-butene copolymerization. Essentially the same slide. The infrared spectra of the polymers. Here you see the band at 1378 from methyl groups. Red, the singly bonded catalyst. Blue, the bridge bonded catalyst. You see that there's much less methyl groups in the polymer that results from the singly bonded catalyst relative to the bridge bonded catalyst. If one butene inserts into the polymer chain, you get ethyl side groups off the main polymer chain, which will increase the number of methyl groups. So what this data suggests is that one butene inserts more readily into the bridge bonded titanium species as compared to the singly bonded titanium species, although some 1-butene inserts into this catalyst as well. And the melting points also reinforce that the more 1-butene that gets incorporated into a polymer, you'll decrease your melting point. Both of these melting points are lower than the ethylene homopolymers, which I showed in the previous slide, and the singly bonded catalyst gives a higher melting point than the bridge bonded catalyst, reflecting more 1-butene incorporation into this catalyst. So, in conclusion, what I've tried to convey is that is a way to pre-modify your silica surface to selectively eliminate certain types of functional groups and then use that modified surface essentially as a template for catalyst synthesis, where you can selectively vary your types of surface species, active surface species on the gel. Apparently the diffuse reflectance technique has caught on in the catalyst community, so that's probably not necessary at this point. Again, we can make predominantly singly or bridge-bonded titanium surface species by selective modification of certain types of functional groups before reaction. The singly bonded titanium surface species are 3.5 times more active to ethylene homopolymerization compared to the bridge-bonded species. And however, the bridge-bonded species seem to incorporate more readily 1-butene. So thank Quantum for allowing me to talk about this. I want to thank Jawad Mirad, who taught me how to handle these air-sensitive compounds, which I didn't know about until a couple of years ago. And thanks for your attention.
Calibration question. What is the activity of that catalyst? Is it just for the method? What is the surface alone? Calibration. You should try to do the sum of the two, or more than that.
The surface, you mean just the silica gel with ethylene?
Well, that you one made a singly bonded titanium trichloride, the other had
what did you have both?
What did you have both?
What you would expect, because you're essentially diluting your singly bonded species and bridge bonded species that would lower your overall activity for inspiration and add. Since the bridge bonded species are not as active, if you have
What are the temperatures of the cyanidation?
that reaction will go through temperature.
Suppose we increase the temperature, we can cyanide even the hydrogen bond effects.
You may be able to get some of them. There are tricks you can do to get some of them. Other organosilanes are more active as you add catalysts.
Not all.
You never get all of them. No. That was since we're running behind. I didn't show a couple of overheads where I showed how you could get all of them. In essence, you can make a silica surface which retains its high surface area and its porosity, but without any reactive functional groups. And I thought somebody in here may be able to use that at some point. But you have to combine the thermal and chemical treatments. You can't do it with just one or the other.
You're not any amount of application of the state modules where you just look at it very
No, it happens with the fume silicas if they're not modified. But the gels disperse very nicely.
Steve?
You copolymerize the butane. Does that change the rate of your polymerization?
Yes, it does. It decreases the flow.
It changes the same for both.
sure, because the bridge bonded catalyst with 1-butene is such a lousy catalyst that I had a hard time getting reliable activity. But it certainly decreases the flow. I don't know.
The monodentate but
That's okay.
monodentate and bidentate titanium complex. After treatment with triethyl aluminum, what's the final catalyst?
Good point. Yeah, good point. I'm trying to figure that out. You know, we're throwing various techniques at it, ESR, NMR, but I have no direct access to that, so I'm just waiting for that sort of analysis to happen. But that's, you know, obviously the next step.
In what way they are different as a catalyst, monodentate and bidentate, because you are observing
And activity.
in what way they are different mechanistically?
Mechanistically speaking, well, that goes along with the characterization. We're going to have to characterize these things, at least electronically, you know, to see if the titanium species are more or less, in what kind of oxidation states they're in relative to their surface bonding after a reaction with the aluminum triethyl. Then maybe we can start making some, at least speculations, but at this point, it would be wild guess.
Are there any other questions?
Do you try any other Tristates compound in the place of titanium?
Not yet. That's coming. But, this is slow going. We're going to try every polymerization active metal we can think of eventually. So we haven't done it yet.
Thanks again, John, for a very interesting talk. It's time for a coffee break. There should be coffee and donuts down in the main exhibition, one level down. Let's be back here at 10:20 in 15 minutes.